Okay, hello everyone. Welcome to our tutorial, which is about the applications, challenges, and approach to language scaling. First, let me introduce the presenters and the content of this tutorial. My name is Daxin Jiang. I'm from the Microsoft Software Technology Center at Asia, or STCA for short. There are three other presenters, Linjun Shou, Xiubo Geng, and Ming Gong. They are also from STCA. And the last presenter is Professor Jian. He's from Simon Fraser University. Okay. In the first part of this tutorial, I will give an introduction to language scaling for NLP applications. We will start with several concrete examples of NLP applications in Microsoft products and services, and then we will describe the problem setting for language scaling. Since there are many NLP applications and they may look quite different, we will propose a systematic categorization so that the applications sharing the same NLP task will be grouped into the same category. And the benefit of such a categorization is to facilitate generalization. That means we can generalize similar approaches to different applications as long as they belong to the same category. At the end of this introduction part, we'll summarize the common challenges for language scaling. Okay, then in the second part, we will briefly describe the major approaches to language scaling, including model transfer and data transfer. Then the major content of this tutorial is in the third part, where we present more technical details for language scaling. Since NLP is such a broad area, we cannot cover all applications. So here we just follow our categorization of NLP applications and select one representative application for one type of NLP tasks. These applications include dependency parsing, machine reading comprehension, and grammar error correction. So my colleagues Xiubo, Ming, and Linjun will present these topics. And if you are interested in more applications, you are more than welcome to refer to a related tutorial from us in this year's the web conference. And finally, in the last part of this tutorial, Dr. Pei will give a summary and propose several future directions for language scaling. Okay, everything needs to have a motivation, right? So before we jump into the technical part, I can come up with the motivation for language scaling from several perspectives. First is from society and humanity perspective. We believe language scaling is invaluable to the advance of social welfare. So here I just lifted the content from the SIL website. I think it perfectly explains why language matters. For example, to eradicate extreme poverty and hunger, achieve universal primary education, to promote gender equality and empower women, to reduce child mortality, and many more. So the importance of language scaling can also be viewed from industry perspective. So here, please allow me to quote the mission statement of Microsoft as example, which says to empower every person and every organization on the planet to achieve more. We can read the needs for language scaling from this statement. In fact, natural language processing has been widely adopted in various Microsoft products and services, including Bing, Azure, Office 365, and so on. So in the following, let's look at several examples of these applications. As the first example, Speller is a key component in Bing and Office. For example, in Bing traffic, around 15% of user queries contain spelling errors. So here are some examples for spelling correction for different languages. So spelling correction for 100 languages actually raises a very interesting challenge. That is, we need to find a balance between scalability versus specificity. Intuitively, when we scale out to many languages, we should consider more about the common features among different languages, because otherwise we simply cannot scale out. For spelling correction, we do have common features like character insertion, deletion, substitution, and transposition. However, we also observe that if we only focus on common features, but completely ignore language-specific features, the quality of our model can never be good enough. One example is the Japanese speller. So there are 4 different types of scripts in Japanese, including kanji, hiragana, katakana, and romaji. And there are 2 different types of input methods. So on PC, people usually use romaji, while on mobile, people use kana. If we don't handle these language-specific features, the speller performance will not be competitive for Japanese. For example, for these 2 Japanese strings, if we just compare the surface characters, they look completely different. However, if we consider the input methods, no matter kana or romaji, they're actually different with just one keystroke. So in speller design, we need to collect language-specific training data, and at the same time, we need to make trade-off between scalability and specificity to meet the highest ROI. That means return over invest. Then the second example is a Bing search relevance. As we can see from these examples, currently the Bing search engine provides web results in more than 100 languages. Now the web ranker in Bing has been powered by deep learning models. So the challenge here is about efficiency. We know that a multilingual deep ranking model often contains hundreds of millions or even billions and now trillions of parameters. So this is a huge model. Then on the other side, the web index contains hundreds of billions of documents. So this is a huge index. Then for each query, we need to rank the top 10 most relevant documents from the huge index by the huge model with a very limited budget, usually only several hundred milliseconds. Therefore, we have to design smart ways to improve the efficiency while still keeping the relevance power of the big model. So the third example is from Outlook. Currently, Outlook can suggest short and relevant replies as shown in these examples if the user's response to the incoming emails only involve generic acknowledgements, greetings, confirmation, and so on. So users can simply click on the suggested replies instead of typing these characters. So this feature can save users time. Suggested reply in Outlook has also been available in multiple languages, as we can see from these examples. So similar to web search, one challenge behind this application is also to compress the huge deep learning models and serve them online with high efficiency. And another challenge for suggested reply is the data privacy issue. So currently, Outlook data for different countries are stored in their corresponding data centers. According to the compliance restriction, this data cannot be moved out of the data center. However, we need to train a universal model to serve all the languages because users in the same region often speak multiple languages. If we only use the data from a single data center to train the universal model, the data may not be sufficient, and we actually waste the data from other data centers. Unfortunately, due to the compliance restriction, we cannot mix the data from all the data centers. So an interesting challenge here is how to fully leverage the data from all the data centers, but without breaking the privacy constraints. Okay, the fourth example is from Microsoft Teams voice assistant. For example, when the user speaks to the sentence to Teams, join my next meeting, the system will conduct a semantic parsing to this sentence. To be more specific, it will recognize the domain for this sentence is calendar, and the user intent is connected to meeting. It will further extract the term next to interpret the start time for the meeting. So after the semantic parsing, the results will trigger the Teams action to join the next meeting for the user. And now Teams has supported a large number of domains for various languages. Then in order to support a large number of domains and a large number of languages, we need to find large amounts of training data. However, as we will explain in later slides, it's usually a big challenge to collect the training data, especially in non-English languages. Moreover, to support semantic parsing for each domain and for each language, we usually need to build a domain classification model, an internet detection model, and a slot tagging model. In practice, we have hundreds of domains and more than 100 languages, so the total number of models will be very large. Such a large number of models present big challenges for model training, deployment, and maintenance. So in the industrial applications, we need to handle both challenges. One is the lack of training data, and the other is to handle a large number of models. Okay. So all the previous applications and challenges are not only interesting to industry, they also attract intensive interest from the research community as well. So if we search for multilingual, cross-lingual, and bilingual in the ACL anthology, which includes the ACL and the EMNLP conferences, we see that the number of papers has been increasing very fast. In particular, in the past 2 years, it has become a very hot topic. Since language really matters, now let us look at a problem description for language scaling. Well, given an NLP application, such as the examples we demonstrated in previous slides, in practice, we usually have relatively rich English training data. And oftentimes, from those English training data, we may result in a well-trained English model. Then our task is to scale out the English model to more than 100 languages. But there are 2 requirements for language scaling. One is the effectiveness, meaning that we have to guarantee the model quality to meet certain criteria. For example, the shipping criteria in terms of precision and recall for our products and services. And the other requirement is efficiency. That means when we handle so many languages, we have to reduce the cost in both money and time as much as possible. Okay, so the previous problem description is clear when the input is a single text. However, when the task involves 2 inputs, there might be some ambiguity. For example, in web relevance, one input is user query, and the other input is web document. So in previous problem setting, we have English training data where both the queries and the documents are in English. Then we transfer to other languages. For example, both queries and the documents are in Chinese. But there could be a related problem setting where the queries are in one language, for example, Chinese, and the documents are in another language, let's say in German. Then this problem also involves different languages. To distinguish these 2 different settings, we call the first setting language transfer and the second setting cross-lingual. However, in the following, we will not explicitly distinguish these 2 settings because both of these 2 settings need the same multilingual representation and cross-lingual alignment. So here we just register that there exist 2 slightly different settings, but the approaches are basically in common. After we introduce the problem setting, we further propose a categorization of various NLP tasks. As mentioned before, the reason for this categorization is to facilitate generalization. That means we may apply similar approaches to various applications belonging to the same category. So at the highest level, the NLP task can be divided into NLU and NLG, which means natural language understanding and natural language generation, respectively. Then NLU tasks can be further divided into classification, sequence labeling, and structure prediction. So in this tutorial, we will cover text pair sequence labeling, structure prediction, and token level text generation in the application part. And in a related tutorial in this year's the web conference, we covered another 3 applications, namely single text classification, text pair classification, and a single text sequence labeling. So if you are also interested in those applications, you are welcome to refer to that tutorial. Before I jump to the technical details, I will use several slides to have a brief introduction to these NLP tasks, in case some audience are not familiar with them. The first task is text classification, and depending on the user input, text classification has 2 scenarios. The first scenario is that the input is just a single text. For example, when the user raises a query, what is the average rain of Beijing in summer to the Bing search engine. One classification task is to tell the domain for this query. For example, whether this query belongs to the domain of a recipe, weather, celebrity, or some other domains. And similarly, another example of a classification task is to assign an intent label to this query among all the predefined user intents, such as check weather, check history, statistics, and so on. Then the second scenario for text classification involves two input texts instead of one. Then the classification task is often regarded to the relation between these two texts. As one example, given two queries to a search engine, we may want to know whether they are paraphrased to each other. And a special case in this category is information retrieval. For example, in web search, one input is user query and the other is web documents. And the task is to rank the documents based on their relevance to the query. So although the ranking task is concerned about the relative order of the documents with respect to the query, here we still consider it as a special case for classification, because essentially the task is to predict the relevance score between a document and a query. Similar to text classification, the task of sequence labeling can also be divided into two scenarios depending on the input. So for single text input, one example for sequence labeling is named entity recognition, or NER for short. So traditional NER only considers person, organization, and locations as entities. But depending on the requirements of applications, we can expand the set of targeted entities. So here is one example to trigger a flight status answer card on the Bing search engine. Given a user query, we need to label various entities, also called slots, such as the departure airport, arrival airport, and the airline company, and so on. So this task is also called slot tagging. So both NER and slot tagging belong to the category of single text sequence labeling. Then for text pair, the example is a machine reading comprehension, where for each instance, we have a question and a passage. Then the problem is to label the answer span with respect to the given query within the given passage. So here is one example from Bing. If you ask what is the date for KDD 2021, the search engine will highlight the answer to this question, which is August 14 to 18th, 2021. The third category of NLU tasks is structure prediction. That means given a sentence, we want to parse the syntactic structure of the sentence. And there are two widely used methods to represent the syntactic structure of sentences. One is called constituency parsing, and the other is dependency parsing. Constituency parsing illustrates how the words in a sentence group into nested constituents, or also called phrases. As shown in the left figure, the structure of a sentence is represented by a tree, which is based on the phrase structure grammar. Then on the right side, dependency parsing emphasizes on how the words in a sentence depend on each other. Each word has a directed edge towards its head, and there is also a label to describe the dependency type. So the task of structure prediction is to predict either the constituency relation or dependency relation of the words in a given sentence. So all the previous three tasks belong to natural language understanding. Now for natural language generation, the subcategories can be divided based on the granularity of output. For example, whether they are at the token level or sentence level. For sentence level generation, the whole sentence is generated by the model from scratch. While for token level generation, not all the tokens in the sentences are generated by the model. So some tokens are copied from original sentence, or some tokens can be given by the users. For token level generation, the examples are spelling correction and sentence auto-completion. So here are some real cases for spelling correction from Bing search engine, as well as some examples for sentence auto-completion from Microsoft Word. And there are also many applications for sentence level generation, such as machine translation and the response generation in conversations. So here are some concrete examples. Based on the previous categorization of NLP tasks, we will look into individual categories with representative applications in the later part of this tutorial. But before that, we would like to summarize several common challenges for language scaling, which are faced by all the NLP tasks. The first challenge is the lack of training data. So for an industry-level application, such as passage QA or web relevance, the size of the human-labeled data for one language, such as English, is often at the magnitude of millions. Apparently, it is unrealistic to label so much data for each language. In fact, some previously mentioned challenges, such as language-specific features, data privacy issues, and cold start problems, are all rooted in the lack of training data. So in the following part, how to address this data challenge will be a major focus of this tutorial. Then the second challenge is how to deal with a large number of models. As we demonstrated in the application of Teams voice assistant in the previous slide, the large number of domains times the large number of languages may result in a large number of models. The challenge is that if we have a lot of models, the cost for model building, serving, and maintenance will also be very large. So to solve this challenge, several studies proposed multitask learning and adapters. But the idea of multitask learning is to share the model parameters for different domains, applications, and languages. Therefore, the number of models can be greatly reduced. However, it is difficult to optimize the shared parameters for individual tasks. So this motivates the idea of adapters, where the parameters are decomposed into two parts. So a majority part of the parameters will still be shared, but at the same time, a small part of the parameters will be grouped into the so-called adapters, and they are fine-tuned for specific tasks. So in this way, it keeps a balance between the maintenance cost for models and the flexibility for individual tasks. Then the third challenge is model size and latency. As we introduced in the application of web relevance, a deep learning model often has hundreds of millions or even billions or trillions of parameters. So these models are just too heavy to be served online. In practice, there have been various efforts to mitigate this challenge, including hardware acceleration, computation library optimization, as well as all kinds of model distillation and compression methods. So in this tutorial, we will not cover the approaches for all these three challenges, but instead we'll mainly focus on the first challenge. That is, how can we scale out to more than 100 languages with a few or even zero training data in the target languages? In order to tackle the challenge of small or zero training data in target languages, the basic idea is to transfer the knowledge from the source language to the target language. In general, there are two transfer approaches. One is model transfer, and the other is data transfer. Okay, so this slide tries to summarize the overview of the approaches and share some of our insights learned from practice. So basically, the central idea of all model transfer approach is to align the representations of different languages so that the sentences with similar meaning can have similar representations, no matter which languages they are in. Then the central idea of data transfer is to synthesize labeled training data in the target languages. Usually, the synthesized data can be derived from either the source training data or the source trained model. So based on these two ideas, there are a lot of methods developed in the literature. Then you might wonder which method we choose in practice, or is there any principle to choose the methods? Unfortunately, there is no single winning method that has the best performance for all tasks. But given the specific task, we have to conduct empirical study to choose the suitable methods. However, there is still some good news. That is, we may refer to the previous categorization of various NLP tasks. We found that if two tasks are similar to each other, which means they belong to the same category or the same subcategory, then the performance of different methods on these similar tasks are usually quite consistent. That suggests that we may choose similar methods for similar tasks. And another observation is that the selection of methods is often constrained by which data are available. There are different types of data that can be used for knowledge transfer, including monolingual corpus, unlabeled data, tree bank, translated data, parallel data, or bilingual dictionary, and so on. So as we will see in later slides, different methods require different data. Obviously, if the required data is not available for some target languages, then the corresponding method cannot be applied. So this is one point we need to pay attention to when we look at individual methods in later slides. Okay, now let us first discuss the model transfer approach. The first step in model transfer is to build a cross-lingual model. So the purpose of a cross-lingual model is to learn the alignment between the representations for different languages, which is illustrated by these two figures. So the upper figure represents the distribution of different languages before the alignment. We can see that they are independently distributed and there is no relation between the words in different languages. And this lower figure shows the effect after alignment. So the similar words in two languages, such as gatto in Italian and cat in English, which have the same meaning, are mapped close to each other in the aligned space. Okay. So after we have a cross-lingual model, then the second step is called a fine-tuning. That means we use English training data to continuously train the cross-lingual model. Since the English training data is aimed at a particular task, so the model after fine-tuning will perform well on that targeted task. So one thing to call out here is that the cross-lingual model has already aligned different languages into a common space, right? Therefore, the features used by this fine-tuned model is actually language agnostic. Then in the test stage for fine-tuned model, given one test instance in a different language, we will apply the same cross-lingual model to map the target language into the language agnostic representation. Then the fine-tuned model will not distinguish from which original language the input is from. Instead, it will just generate the result uniformly for all languages. So in a short summary, the model transfer approach consists of 3 steps. First, we train a cross-lingual model to align different languages. Second, use the English training data to fine-tune the model. And then lastly, apply the same cross-lingual model to generate language agnostic features and feed into the fine-tuned model to derive the final result. Among all these 3 steps, the most critical one is the first step, where we train a cross-lingual model to align different language. So that's also the reason why this approach is called model transfer. So in the following, let's have a review of various cross-lingual models. At a high level, we distinguish 2 types of cross-lingual models, depending on how the languages are represented. So the first type represents languages by word embedding. So it is called cross-lingual word embedding. And the second type represents languages by contextual embedding. Accordingly, it is named as cross-lingual contextual embedding. So in the following, let's look at more details of these 2 types one by one. So for cross-lingual word embedding, at the first level, it can be divided into mapping-based methods and joint learning methods. So for mapping-based method, it usually has 2 steps as indicated by the numbers 1 and 2 here. So the first step is to learn the word embedding for each individual language independently. And then the second step is to learn a mapping matrix between 2 language embeddings. So in this formula, XS and XT in the first part denote the word embedding matrices for the source and target languages respectively. Then L is the loss function for learning the word embeddings. Then in the second part, omega is the loss for the mapping matrix W that aligns XS and XT. Then in the joint learning method, the word embedding loss and the alignment loss are optimized at the same time. That means both languages share the same vector space so that the words with similar meaning in different languages are mapped as close as possible in this shared vector space. So it is actually quite obvious to differentiate these two types of methods. We just need to check when the language alignment happens. If the alignment happens after the word embedding, then it is mapping-based method. Otherwise, if the alignment happens at the same time with the word embedding, then it is a joint learning method. So both mapping-based methods and joint learning methods can be further divided into smaller categories. In this tutorial, we will not cover the details, since Radar et al. Already have a great tutorial and a survey paper for these various methods. So we refer the audience to these materials. So word embedding learns the encoding for individual words. Although it is lightweight and effective, a big limitation is that it can hardly address the issue of word ambiguity. We know that many words have multiple senses. In order to accurately capture the meaning of words in sentences, we need to take context information into consideration. So that's the motivation for contextual embedding models. So this figure summarizes various approaches to cross-lingual contextual embedding. Similar with cross-lingual word embedding, at a highest level, cross-lingual contextual embedding methods can also be divided based on the time when the alignment between languages happens. So if the alignment happens simultaneously with the learning of contextual embedding, then it is a joint learning method. Otherwise, if the alignment happens after the contextual embedding for individual languages, then it is called a retrofitting method. For these two types of methods, the mainstream for cross-lingual contextual embedding is joint learning methods. And there are only a few works belonging to retrofitting methods. So let us first take a closer look at joint learning methods. Joint learning methods can be further divided into two subtypes, depending on whether they need parallel data for alignment. So for the methods which need parallel data, we summarize the three major ideas: neural machine translation-based approach, called NMT-based, dual encoder, and language model-based approach. So in this introduction part, we'll pick up one example for each approach to briefly introduce the major idea at a high level. And we'll also highlight the major differences among these various methods. But we leave the technical details and more related work for each of these approaches in the third part of this tutorial when we deep dive into concrete applications. Okay, so a representative work of neural machine translation-based method is by Arteaga and Jiang. So the basic idea is to apply a encoder-decoder architecture for machine translation. To be more specific, the encoder part takes in a sentence in the source language and encodes it into a sentence embedding vector. Then based on this vector, the decoder part will generate the translation of the input sentence into the corresponding target language. So this is the standard sequence-to-sequence neural machine translation architecture. Then you may wonder why this neural machine translation architecture can be used to train cross-lingual models. The idea is to apply many-to-many translation. To be more specific, there are multiple source languages at the input side, but there is no indicator to distinguish the input languages. In other words, all the information that the decoder can see is the sentence embedding vector generated by the encoder. Therefore, this setup implicitly enforces all the input languages to have a uniform encoding. So this is the basic idea for NMT-based method. And there are more variations for this idea. And we'll introduce more details in the later part. Different from the previous NMT-based approach, the dual encoder approach adds explicit constraint for language alignment. So here, let us look at the work from Guo et al. As a representative to explain the idea. So suppose X and Y are two sentences in two different languages. Each of them goes through a stack of hidden layers and then gets an encoding vector. let's see U and V, respectively. Then there is a scoring function phi xy to evaluate the similarity of x and y. For example, in Guo et al.'s paper, the authors applied the dot product of U and V as the scoring function. So in order to train a cross-lingual embedding, we can leverage the parallel data as the training data. So if y is the translation for x, then the score of phi xy is high. Otherwise, the score is low. So in this way, the embeddings of different languages are aligned to the same space. Again, there are several follow-up works based on the dual encoder idea, and we will present more details in the later part. A third type of contextual cross-lingual models usually employ transformers to learn language models. So the major difference between this approach with the previous two approaches lies in the granularity of cross-lingual units. Please note that in the previous two approaches, the models aggregate the word representation into sentences, right? So the unit to transfer across languages is a sentence embedding. However, in transformer-based language model approach, we can find cross-lingual representation at both sentence level and token level. For now, let's just be aware of this key difference, and we'll describe the technical details in later part of this tutorial. The common point for the previous three approaches is that they all reply parallel data for language alignment. However, in practice, it is usually expensive to collect parallel data, especially for resource-low languages. There may not be parallel data available. So some recent works have shown that we may not necessarily need parallel data to learn cross-lingual models. So in the following, let's look at some examples. So multilingual BERT, also called MBERT, is probably the first work that does not use parallel data to learn cross-lingual representations. In fact, the multilingual BERT model shares the same architecture and the training scheme with the monolingual BERT model. The major differences are in the training data and the vocabulary. So for monolingual BERT, the vocabulary contains English words only, and the model is trained by pure English data. In contrast, the multilingual BERT is trained by Wikipedia pages in 104 languages, and the vocabulary contains 110,000 word piece tokens covering all the 104 languages. So the amazing thing here is that although the whole training process for multilingual BERT does not carry out any explicit or implicit alignment across languages, it still shows very good cross-lingual capability. So many works explored why MBERT has cross-lingual effectiveness. Earlier works attributed the cross-lingual capability to vocabulary overlap among different languages. For example, the Latin family languages share many cognate words. And even for distant languages, such as Chinese and English, the text still contains some English words, such as CPU, GDP, and so on. So these shared words act as the anchors to align different languages. However, some later works disclosed more evidence that shared words are not the reason, or at least not the only reason for cross-lingual capability. So one study showed that MBERT still has cross-lingual effectiveness even when there is zero vocabulary overlap. Therefore, some studies postulate that the cross-lingual capability may come from the common structure in different languages. For example, many languages share the subject, verb, object, word order, and the distribution for the most frequent words in different languages could also be similar to each other. But if you are interested in this topic, I list several related works for your reference. Okay. Multilingual BERT is a language encoder, so it is mainly used for language understanding tasks. Correspondingly, for language generation tasks, an example model that does not use parallel data is called multilingual BART. MBART and MBERT is different in only one character. Please don't confuse these two models. MBART is for language generation, while MBERT is for language understanding. So the idea of MBART is actually very similar with that of MBERT. So the multilingual BART shares the same model architecture and the training scheme with the monolingual version, and the differences are mainly in training data and the vocabulary. So the monolingual version contains only English data and English vocabulary, while the multilingual version contains mixed language data and a comprehensive vocabulary to cover all the languages. Okay, so all the previous methods are joint learning methods in the sense that the cross-lingual alignment is learned at the same time with contextual embedding. So in contrast, the retrofitting methods build the cross-lingual alignment or enhance the alignment after the learning of contextual embedding. So in the following, let's also look at the two representative methods. The first method is called contextual token mapping. The idea is very similar with the previous mapping-based cross-lingual word embedding. We know that for word embedding, each word in the language has a fixed embedding, which does not change with the context of the word. Then in mapping-based cross-lingual approach, we learn a matrix W, which maps the word embedding from one language to another language, so that the embedding vectors of the aligned words have the minimum distances. Moreover, to make the mapping more robust, it is often helpful to regularize W to be orthogonal matrix. The major difference between the contextual token mapping and the static word mapping is the sampling methods for the aligned words. In static word mapping, the word pairs are sampled from bilingual dictionaries without considering the context of the words. But in contextual token mapping, the vectors for xi and yi are sampled from the occurrences of the words in the parallel sentences. Therefore, this sampling approach actually takes the contextual information into consideration. Each token vector only represents a single non-ambiguous sense of the word. Therefore, this mapping is expected to be more accurate. The second retrofitting method, which is called model fine-tuning, does not learn explicit mapping matrix W between two languages. Instead, it uses the parallel data to fine-tune the parameters of multilingual BERT so that aligned words in parallel sentences become closer to each other. So here, the upper figure shows the effect of a base multilingual BERT, while the lower figure shows the effect after fine-tuning. We can see that the aligned words are dragged even closer to each other in the lower figure. This idea is formulated by the loss function on the right side. So in this loss function, F is the MBERT model, and C is the parallel corpus. So for each pair of parallel sentences, S and T in the corpus C, we want to minimize the distance between the representations for the aligned words I and J in the parallel sentences S and T, respectively. So back to these two figures, for the base MBERT model, where no minimization process is applied, the distance between the aligned words are still pretty large. Then through this minimization process, also called the fine-tuning process, the distance becomes much smaller. And one detail here is that in order to avoid a trivial alignment, for example, the encoding function F always output constant vectors. The author added a regularization factor, which requires the change to the original encoding from the base MBERT is also minimized. Okay, so this is the whole picture for the various cross-lingual models. In this tutorial, we mainly focus on the contextual embedding models, which is the right subtree of the root node. Because for the embedding, there is already a very good tutorial and a survey. So in previous slides, we briefly introduced the major ideas of various models, and we highlighted the common and the different points for these models. Then in the next part of this tutorial, we'll come back with more details for all these methods and models, and we'll also demonstrate how these models will be applied to specific applications. In addition to the model transfer approach, another approach to language scaling is data transfer. Then you may say that given we already have so many cross-lingual models, why we still need a data transfer approach? The reason is that languages are extremely complex and there exist huge differences between different languages. For example, they may have very different vocabularies, morphological rules, syntactic structures, and so on. So such complex difference may not be fully captured and well aligned by the cross-lingual models. And in practice, even when we apply the cross-lingual models, we often observe big gaps in model performance on English test data versus on other languages. Therefore, we may consider data transfer as a complementary approach to model transfer approach. So in data transfer approach, the central idea is to transcribe the knowledge either in the source training data or in the source model into the training data of the target languages. As we will discuss in the later slides, there are 4 types of methods to transcribe the knowledge, including machine translation, semi-supervised learning, weakly supervised learning, and the data generation. Sometimes the transcription process may also leverage some auxiliary data, such as unlabeled target data, user feedback data, or entity data, and so on. So after we derive the training data in targeted languages, the remaining step is straightforward. That is, we simply use the training data in target languages to train the target models. In fact, the model transfer approach and the data transfer approach are not exclusive. In practice, they are often combined. So this is the method for model transfer process, as we described before. So we result in a fine-tuned model that takes in language agnostic features. So after model transfer, we can further apply the data transfer methods, which derive the pseudo training data in target languages. And in the next step, we continue training the fine-tuned model with those pseudo training data and derive an enhanced model. And then finally, the enhanced model is used to handle the test data in the target languages. So this is how we combine the model transfer and the data transfer approaches. Now let us look at the various data transfer methods, starting with the machine translation approach. So for the purpose of language scaling, there are 2 directions of machine translation. So one direction is to translate the training data in the source language into the target language. This direction is called translate on train. For example, suppose the source language is English and the target language is Hindi. We can apply machine translator to translate the English training data into Hindi training data. Then after translation, we usually need to further apply the sentence alignment methods to derive the labels from the source instances to the translated instances. Then in the third step, we use the translated Hindi data with the labels to train Hindi models. So this process follows the standard flow we introduced in the previous slides. So please note that in this whole process, the machine translation, sentence alignment, and the model training steps are all carried out at the offline stage. Then at online stage, we directly use the Hindi model to do the inference. In fact, for machine translation methods, there exists another translation direction, which is totally opposite with the previous flow. This opposite direction is called a translate on test. We also introduce this direction for a reference. So as the name suggests, translate on test means the machine translation happens at the online test stage, and the translation direction is from the target language to the source language. Again, let's suppose the target language is Hindi and the source language is English, and we already have an English model trained from the English training data. Okay. Then given a Hindi test case, we apply machine translation online to translate it into an English test case. Okay, then we can apply the English model on this translated English test case to get a result. And finally, we further align the English test case with the Hindi test case to derive the label on the original Hindi test case. So this is the flow for translate on test. In practice, most applications prefer translate on train rather than translate on test. The reason is that translate on test needs extra time for machine translation and sentence alignment at the online inference stage. So for many online services, latency is very critical for user experiences. Therefore, we usually adopt the translate on train approach to reduce the online latency as much as possible. The machine translation approach assumes there's a translator between the source language and the target language. However, for some target languages, the machine translator may not be available. In such cases, we may consider whether it is possible to collect unlabeled data in target languages. For example, for the task of machine reading comprehension, we can easily collect a large volume of queries and passages in 100 languages from the Bing search engine. So once the unlabeled data in the target language is available, we may carry out semi-supervised learning. So in the first step, we can leverage the previous model transfer approach to derive an initial model. Then in the second step, we can apply this initial model to the unlabeled data in a targeted language. Consequently, for each unlabeled instance, we now have the labeling result, which is generated by this initial model. That means the unlabeled data becomes labeled data now. So in the next step, we use this labeled data to retrain the initial model, and this process can be iterated for several rounds. Intuitively, if the initial model can derive reasonable labeling results, then after we apply it to convert the unlabeled data into labeled data, such extra training source can help to improve the model quality. Then in the next round, the model with improved quality can further generate even better labeling results. And this iteration gradually improves the model performance round by round. In practice, in order to guide the iteration towards better labeling results and better models, we may adopt some techniques such as self-learning, model ensemble, and reinforcement learning. So we'll also cover more details for these techniques when we talk about machine learning comprehension in the later part of this tutorial. In addition to unlabeled data, sometimes it may also be possible to collect various auxiliary data to help with targeted tasks. So these auxiliary data may provide indirect signals to supervise the learning process. That's why they are called weakly supervised learning methods. So in the following, let's look at two examples to illustrate the idea. So one example is question answering for Bing. So let's reuse the previous example. When the user asks the question, what is the date for KDD 2021? The Bing search engine will provide this passage and highlight the answer at the top position in the search result page. Then how do we know whether this passage is relevant to the user question or not? So from the search engine logs, we can collect rich user behaviors. For example, how long the user dwells on the search result page, whether the user clicks on the URL in the question answering block, whether the user reformulates the query, whether the user clicks on web documents outside of the question answering block, and so on. Although each single user behavior is a weak signal for the relevance of this passage, when they are combined in a machine learning model, the prediction accuracy can be very high. So in our empirical study, we find the users all over the world have similar behavior patterns. That means this method is generally applicable to all languages. Therefore, in this way, we can cheaply collect a large amount of training data for all the languages. So this is one example. We collect user feedback as a weekly supervision signal. Another example also comes from question answering scenario for Bing. So after we provide the relevant passage for user question, we need to further highlight the answer span in the passage. For the previous example, the highlighted span is August 14 to 18, 2021. So this task is called machine reading comprehension, or MRC for short. So one challenge for MRC is to accurately detect the boundary of the answer span. So here are two examples. So in the upper example, the ground truth is King David, but the predicted answer exclude some actual irrelevant words. And in the lower example, the ground truth is 50 to 100 milligram, but the predicted answer is just 100 milligram. So it misses some useful words. In order to address this boundary detection challenge, one idea is to use large amount of entity data to pre-train the MRC model. In other words, we mask the whole entities in the sentences and let the model recover the full entity span. Since many answer spans are constituted by entities, such pre-training can effectively improve the accuracy of boundary detection. So in this example, the entity data serves as the auxiliary data, which provides weak supervision signals to the MRC model. Since the entity data can be automatically mined from the web, this method is also generally applicable to all the languages. The last commonly used data transfer method is data generation. The idea is actually very straightforward. Since we lack the training data in the target languages, we try to synthesize some training data to approximate the real data. Then the problem becomes how to build a cross-lingual data generator. In practice, different applications have different forms of training instances. So the data generators will also be different accordingly. Here, I just use one example task to illustrate the idea. To be specific, the example is a natural language understanding, or NLU for short. So the task of natural language understanding predicts the intent of user input, and at the same time, it also labels the important slots in the input. For example, when user input PVG to SFO Delta flight status, the intent is to check flight status, and there are 3 slots to be labeled, as shown in this figure. This NLU task often serves as a key component in task-oriented dialogues. And from the terminology of dialogues, the intent plus the slots are often called a dialogue act. So we can also say that NLU task is to derive a dialogue act given the user input. Okay, so to generate the synthetic training data for this NLU task, the input is the dialogue act, and the output will be a sentence corresponding to the dialogue act. So this task is called NLG, natural language generation. So now we have both NLU task and NLG task at hand. And these two tasks are highly correlated. So let us review again their relation in order not to confuse them. Please note that the NLU task is our primary problem. The input is a user sentence and the output is the dialogue act. And in order to generate the training data for the NLU task, we need to introduce the reverse problem, which is NLG. So in NLG task, the input is a dialogue act, and the output is a synthesized user input. So once we have an NLG model, we can apply it to generate many pairs of user input and dialogue act. And these pairs are exactly the training instance for the NLU task. Okay, I hope the relation between NLU and NLG is clear now. Then the problem is how to build an NLG model. One example is Peng et al.'s work. So the authors apply a GPT model to fulfill this task. So you can find the details in the paper if you are interested in the generation process. And some works consider the NLU and NLG tasks as a pair of dual problems, where the input of one task is the output of another task, and vice versa. And they develop dual learning methods to enhance the performance of both tasks. Again, I will skip the details here, but list the reference paper. Okay, so in previous slides, we introduced the 4 different types of data transfer methods. So here, let's have a brief summary. Remember that the central idea of data transfer is to produce pseudo training data, which is the pair of X and Y in a target language, where X is the set of training instances and Y is the corresponding labels. So we can compare the different methods through the perspectives of how X and Y are produced. First, for machine translation, we translate the training data from the source languages to the target language. So the data instances are derived from translation, and the labels are derived from the alignment between the translated pairs. For semi-supervised learning, we leverage the unlabeled data in the target language. So the data instances are real data. And in order to generate the labels, we can apply an initial model, which is derived from the model transfer approach to the real unlabeled data. So in practice, we often iterate the process for several rounds and improve the model quality and the label quality in turns. For weakly supervised learning, we also use the real unlabeled data in the target languages as the training instances. In order to derive the labels, we leverage some auxiliary data and extract weak supervision signals. So some examples of auxiliary data could be user feedback or entity data. And the last method is data generation. So in this method, we usually generate the labels first using some heuristic rules, and then we build a data generator to synthesize the training instances based on the generated labels. Okay, so far we have finished the introduction part, and we also had an overview of the methodology, including model transfer and data transfer. So in the next part, let us drill down into 3 concrete applications and discuss more technical details. First, my colleague Xiubo will talk about dependency parsing.
Hello everyone, my name is Xiubo Geng. I'm from the NRP group of Microsoft STCA. Nice to meet you online. So in this session, I will talk about cross-lingual dependency parsing. So this is the outline of this session. First, I will give some brief introduction of dependency parsing, including its definition, evaluation metrics, and the widely used approach for monolingual dependency parsing. Then I will talk about the model transfer and data transfer approach for cross-lingual dependency parsing. Okay, let's look at the definition of dependency parsing. Given a sentence, we aim to pass it into a dependency tree. A dependency tree is a directed graph G, which consists of a node set of V and an arc set A. Here, nodes in V are words of the given sentence, and arcs in A takes the form of a tuple with Wi, L, and Wg. Here, Wi and Wg are nodes in the graph, and L is the label of the arc. For example, in this dependency tree, I and prefer are 2 words and nodes in the graph, and there is an arc from prefer to I, and the label of the arc is unsubj. To echo the taxonomy of NLP tasks in Daxin's slides, we can see that dependency parsing is a structure prediction task with single text as input. Similar to other NLP tasks, we usually have rich annotated data for some popular languages, such as English. However, when we scale it to other languages, we often face the challenge of lacking annotated data. So cross-lingual dependency parsing aims to tackle this challenge. It derives parsing models for low-resource languages, given treebacks of rich resource languages. A popular benchmark used for this research community is the universal dependencies, also known as UD. So UD is a framework for consistent annotation of grammar for over 100 languages with nearly 200 treebacks. Here, a treeback refers to a parsed text corpus that annotates syntax or semantic structure. Since UD provides consistent annotation for different languages, it greatly facilitates It greatly facilitates research of cross-lingual semantic parsing and provides a good testbed to evaluate the effectiveness of cross-lingual transfer. There are two popular used evaluation metrics for dependency parsing, LAS and UAS. LAS is defined as the percentage of words that get the correct head and label, and UAS is the percentage of words that get the correct head. So LAS evaluates the correctness of both head and arc relation. And UAS only cares about whether we can find the correct head for each word. Since cross-lingual dependency parsing relies on monolingual approaches, here we give a brief introduction of a popular graph-based parsing approach for monolingual dependency parsing. Specifically, given a sentence, it defines a space of candidate dependency trees and learns to score candidate trees in training phase. Then in inference, it passes a sentence by finding the dependency tree with the highest score. The scoring of a candidate tree is usually factored into subgraphs. And arc factor model is a popular factor approach. Here, each arc is a separate subgraph, and the scoring of a tree is defined as the scoring of all arcs. As shown in this figure, give a graph G, its score is defined as the sum of all the scoring of its arcs. Here, S is the score of the arc composed of Wi, L, and Wg. In inference, we usually first pass and derive an unlabeled tree, which can be viewed as finding a head for each word. Then for each word with its predicted head, we label it with a predefined category set. So we need two scoring functions. The first one is the S-arc. It evaluates the scoring of an unlabeled arc, Wi and Wg. And it can be used to find a head for a word, and thus can construct an unlabeled tree. Another scoring function is S-label. It is used to predict the label of a given unlabeled arc, consists of Wi and Wg. Now the problem is formulated as learning two models, an unlabeled arc prediction model, which predicts the head of each token, and a label prediction model, which predicts the label of a given head-dependent arc. A widely used approach for these two functions is the Bayesian attention model, proposed by Daxin and Ming in 2017. Let's take the unlabeled arc prediction model as an example to demonstrate how it works. First, each input sentence token is embedded into a vector xi. Then we get the vector ri by applying a bias term on xi. Then on top of it, we apply two different MLP and get two vectors, each depth and each head. Here, each depth represents the embedding when the current token is dependent of an arc, and each head represents the embedding when the current token is ahead of an arc. Next, for each candidate arc, I and J, which compose of a token I and token J, and represent the arc from J to I. We evaluate its arc score by applying a Bayesian attention model on two vectors, each depth of token I and each head of token J. So the biaffin function is defined as in this equation, which is basically extending the bilinear function with an additional linear function or input vectors. To summarize, the basic idea of biaffin attention model is that for each token, we derive two different vectors, h arc depth and h height. Then we use the depth vector of token I and height vector of token j to evaluate the score of the candidate arc. Similar to the unlabeled arc model, we can also use another biaffin attention model to predict the label of each arc. Here we will omit the details for label prediction model. In the training phase, we learned the two biaffin models. At the inference, we first pass the input sentence into an unlabeled dependency tree using the unlabeled arc prediction model. And then we predict the label of each arc according to the label prediction model. Okay, that's the introduction or background. Now let's talk about cross-lingual dependency parsing. Basically, there are two major paradigms, model transfer and data transfer. Let's first look at the model transfer approach. So cross-lingual dependency parsing has a long history. Before multilingual embeddings are derived, a popular approach for model transfer is to train a delexualized model. The basic idea is simple. Given a source language treeback, we first delexualize the input sentence into part-of-speech features. As shown in this figure, the sentence "John likes the blue house" is delexualized into a sequence of part-of-speech features. Then the delexualized dependency tree is used as training data to learn a parser. And the learned parser can be directly used for target languages. We can see that the delexualized model does not rely on language-specific lexicon, and it only uses shared part-of-speech features across languages. So it shows some success for closely related languages. However, since the part-of-speech features only carry some coarse-grained information, its performance is limited, especially when the target language and source language are far away from each other. So many researchers have investigated more features to provide additional information, such as typological features and cross-lingual word clusters. Here are some examples of typological features. For example, this one represents the order of subject, object, and word in the language. Such features indicate language-specific typology, so it can be used to select shared model parameters when there are multiple source languages. Another approach is to use cross-lingual word clusters. The basic idea is to cluster similar tokens in different languages into a group. For example, in this table, the English words in the first line and the Spanish words in the second line have similar meanings, and thus they share the same cluster. We can see that such word clusters can remove fine-grained information compared to part-of-speech features. So introducing features derived from cross-lingual word clusters have been shown to significantly improve the accuracy of cross-lingual structure prediction. Here I will not provide more details, but if you are interested in the typological features and cross-lingual word clusters, here are some references. Recently, a multilingual pre-trained model have been developed and shown their effectiveness on many NLP tasks. As discussed in Daxin's session, those multilingual models generate language agnostic embeddings. So a natural solution is the zero-shot model transfer, which means we first learn a model from source language treebacks, and then we directly apply it to target languages. In Wu and Drizel's work, they evaluate such zero-shot approach using M-BERT dependency parsing. The results are shown in this figure. So here, the first column, dist, represents the word order distance of a language to English, and the rows of different languages are sorted according to the difference. The baseline model uses dictionary supervised cross-lingual word embeddings, while M-BERT Z uses pre-trained context-aware multilingual embeddings in a zero-shot manner. We can see that both the baseline and M-BERT performs relatively well for zero-shot model transfer. In another aspect, compared to M-BERT S, which is supervised learning for each language, we can see there is still a large gap, especially for those languages with large distance to English. For example, in this row, we can see zero-shot transfer from English to Chinese using M-BERT only achieved 53 point UAS and 26.8 LAS. In contrast, we can achieve more than 20 UAS and LAS when there is training data for Chinese. So to summarize, pre-trained language model embeddings increases the accuracy of model transfer compared to traditional delexualized approach, while zero-shot model transfer still lags far from supervised learning. So a promising and potential way to improve that is to involve data transfer approach. So next, we will describe two popular data transfer approaches for cross-lingual dependency parsing, namely translation-based approach and unsupervised approach. Let's first talk about translation-based approach. A widely used translation-based approach is called annotation projection. In this approach, we are given a word-aligned paracorpus and a source language parser. There are three steps. First, we annotate the source sentence using the given parser. Then we use the word alignment in the paracorpus to map the source annotation to target sentences. Finally, we train a target language parser with the projected annotation. Another translation-based approach is called treeback translation. The idea is also straightforward. So as shown in this figure, given a source language treeback and a sentence translator, we first translate source sentence into target sentences with the translator, and we also get word-to-word or phrase-to-phrase alignment. Then we map source annotation to target sentences. Finally, we train a target language parser with the projected annotation. So here is a comparison between the annotation projection and the treeback translation approach. First, they require different data. Annotation projection requires para-sentence pairs, while treeback translation requires annotated source treeback. Second, they require different models. Annotation projection requires a source annotator, while treeback translation requires a source-to-target translator. Therefore, the source language annotation is derived from an annotation model, while it is annotated by human annotators in treeback translation. The target language sentences are usually created by human in annotation projection, while they are generated by a translation model in treeback translation. However, after getting a paracorpus and source annotation, both approaches require to map the annotation from source language to target language. So let's look at the projection strategy. This is achieved with the help of word alignment between source and target languages. Here we describe a popular projecting strategy. So if the alignment between the source and target languages is one-to-one, we can directly copy dependence relations from source to target. For example, in this paradata, source 1 is aligned to target 2, source 2 is aligned to target 1. And there is an arc from source 2 to source 1. So we can copy the arc to the target language sentence from target 1 to target 2. If some source languages are not aligned to any target languages, for example, the token source 2 is in this data, there is no target language token aligned to it. In this case, we will add a dummy node, and then we copy arcs from source to target. In addition, if some target words are not aligned to any source words, they will be deleted from the tree. If there are multiple source words aligned to the same target words, we will find the head of all source words and only remove alignments between other source words and target words. In this example, both source 3 and source 4 are aligned to target word 3. And we can see that source 3 is the head of source 4. So we only keep the alignment between source 4 and target 3 and remove this alignment. Now it becomes one-to-one alignment, so we can directly copy arcs from source side to target side. If one source word is aligned to multiple target words, for instance, here, source 1 is aligned to 2 target words, target 1, target 2, we take the following steps. First, we introduce a dummy node. Then the dummy node acts as the immediate parents as those target words. And finally, the dummy nodes capture the dependency relations of the source side annotation. For those many-to-many alignment, we first apply one-to-many strategy and then apply many-to-one strategy. Okay, that's all for the strategy. That's all for the projecting strategy. Overall speaking, the translation-based approach synthesizes target language data for model training. It achieves competitive performance to cross-lingual models. And more importantly, they can be combined with cross-lingual models and further improves the performance of cross-lingual transfer. However, they also have limitations. First, there is not always perfect alignment between source and target words. For example, in this case, the English word I, being, and the Swedish words mate, they don't have any corresponding word level translation. Second, the translation error in treeback translation or the parsing error in annotation projection will also be propagated to target sentence annotation. Third, it is possible to derive conflicting annotation in the final annotation of target language. So one possible solution to solve these problems is to use code mix treebacks. This is an improvement over treeback translation. The idea is, instead of translating all source language words into target language, we only translate those with high confidence alignment. And additionally, continuous spans of target words are reordered according to sentence translation. So this idea can be illustrated in this figure. Here is the English sentence with annotation and the alignment between English and Swedish. This subfigure A shows full translation, while in subfigure B, the authors propose to partially translate some high confident English words to Swedish. We can see that in the final sentence, some words are English and some words are Swedish words. The code mix approach makes the best use of syntax, source syntax. In one aspect, it tries to introduce minimum noise. In another aspect, it tries to capture the structure of target language sentence as much as possible. So here are comparison results on the universal dependency treebacks. Here English is used as source language. Dialects refers to traditional dialectalized approach. Part purge is a modified treeback translation approach. The idea is to keep only those target language annotations with high confidence. Here, source refers to train a model only on source English treeback, and target refers to train only on translated target sentences. Source plus target refers to training on both English and translated target sentence, and here mix refers to the proposed code mix approach. We can see that all this lexicalized approach outperforms the delexicalized model, showing the effectiveness of lexicalized features. And also the code mix approach can significantly improve the accuracy of cross-lingual transfer, especially when it is combined with, when the training data is also combined with source treeback. So one limitation of translation-based approach is that it relies on a source-to-target translator. However, the translator is not always feasible. So there are also some research works investigating to leverage unannotated target data without any translator. Lu and al. Proposed to use a source reordering approach. The basic idea is give a source language treeback and an annotated target language corpus. It reorders, it rearranges the order of source sentence to meet the word order in target language. As shown in this figure, the original English sentence, "I had a surgery routine," is reordered into "I a surgery routine had." So this is achieved with the guidance of a target part-of-speech language model. Specifically, it first learns a language model on the part-of-speech features from the unannotated target language corpus. The language model is denoted as p-tau. And p-tau takes the permutation of part-of-speech of sentence as input and predict its probability. Then it selects the the permutation of source sentence X with the largest probability. So given P tau, how to find the best permutation is an NP-hard problem. The authors proposed a genetic algorithm to find a near optimal permutation. I will not cover too many details here, but if anyone is interested in it, here is the reference. Another unsupervised approach is direct adaptation. Zhou et al. Proposed an unsupervised cross-lingual adaptation approach to leverage the unsupervised parser based on CRF autoencoder framework. The basic idea is as follows. It first trains a source parser and then uses it to initialize and regularize a target parser. And then it conducts unsupervised training on unannotated target language data. So the critical component in this approach is the CRF autoencoder. The idea is illustrated in this figure. First, each word and its part-of-speech feature is encoded by an encoder to predict the index HI and part-of-speech PI of its head. Then a decoder is employed to predict the part-of-speech of the word I based on HI and PI. So here, the input of the encoder is denoted as Xi, and the output of the encoder is denoted as Y. And the output of the decoder is denoted as X hat. So here, X and X hat are always known. In the supervised setting, the immediate result Y, which is the index and the part of speech of head of the word, is known. So we can learn the encoder and decoder network by maximizing this probability. The probability of the golden Y and X hat given X. In the unsupervised setting, Y is unknown. But we can also conduct model training for encoder and decoder by minimizing this loss function, where we find the maximum probability of P of Y and X hat given X over all possible Y. So to summarize, the encoder and decoder framework can be trained in both supervised and unsupervised setting. Given that, the cross-lingual adaptation is conducted as follows. First, we train a CRF autoencoder in the supervised way with multilingual BERT. Then we use the source model to initialize a second CRF autoencoder. Finally, we train it in an unsupervised way on unannotated target data with regularization by the source model. Okay, this is a summary of all data transfer approach. From the perspective of required resource, treeback translation requires a source treeback plus a translator. Annotation projection requires paradata plus a source annotator. And source reordering and unsupervised adaptation only requires source treeback plus unannotated target sentences. From the perspective of training data, treeback translation generates the target language sentence, while annotation projection gets that directly from paradata. But both treeback translation and annotation projection derives the label by aligning source treebacks to target sentences. In contrast, source reordering directly uses source language sentences and reorders it according to an unannotated target corpus. The label is directly copied from source treebacks. The unsupervised adaptation approach uses real target language data and does not require any labels. Okay, so this is the key takeaways for cross-lingual dependency parsing. First, dependency parsing passes a sentence into a dependency tree, which can be formulated as predicting heads and X labels for each token. Second, traditional model transfer approach leverages delectionalized feature, while modern approaches relies on multilingual embeddings. Third, translation-based approach aligns annotation from source language to target language, which requires a translator or parallel corpus. In contrast, unsupervised approach directly use unannotated target language corpus. That's all for the cross-lingual dependency parsing part. Next, Ming will talk about cross-lingual machine reading comprehension.
Hello everyone, I'm Ming from NLP Group, STC of Microsoft. Nice to meet you online. In this session, I will talk about a sequence labeling task, mainly taking machine reading comprehension as example. Here is the outline. Firstly, to recap, I will give a brief overview of sequence labeling applications. Then, taking cross-lingual MRC task as example, we will go through three aspects, including the task definition and benchmark datasets, the baseline approach, and the related challenges. To address these challenges, the advanced approaches will be introduced accordingly. Finally, the key takeaways will be summarized. Sequence labeling is also belonging to NLU applications. The task of sequence labeling can also be divided into two scenarios depending on the input, that is, single test sequence labeling and test pair sequence labeling. Here are some example tasks for both scenarios. For single test input, one example for sequence labeling is named entity recognition, or short for NER. Traditional NER only considers person, organization, and location as entities. But depending on the requirement of the application, we can expand the set of target entities. Here is one example to trigger a flight status card on Bing search engine. Given a user query, we need to label various entities, also called slots, such as departure airport, arrival airport, and the airline company, and so on. For test pair input, the example is extractive machine reading comprehension, where for each instance, there are a question and a passage. Then the problem is to label the answer span with respect to the given query within the given passage. Here is an example from Bing. If you ask, when will the KDD 2021 be held? The search engine will highlight the answer in the relevant passage to this question, which is August 14 to 18, 2021. In the rest part of this session, we will take MRC task as example to introduce the language scaling approaches. Before 2020, there were few benchmark datasets for cross-lingual MRC. There were mainly three datasets published in 2020, including ML-QNA, Tidy-QNA, and squad. Here are some examples from ML-QNA, which are commonly used in related work. For each instance in ML-QA, it contains a query and a passage, and the goal is to extract the precise answer span from the passage, like the orange highlighted phrases here. ML-QA contains QA instance in 7 languages, including English, Arabic, German, Spanish, Hindi, Vietnamese, and simplified Chinese. The typical experiment setting with this dataset is, for model training, only English label data is used, without other language-specific labeled data. After training, directly test the model on non-English language test sets. To build up the cross-lingual MRC model under this typical setting, there are two baseline approaches on top of the cross-lingual pre-trained model. One is zero-shot training, which only use English labeled data to fine-tune the cross-lingual pre-trained model and directly test on the non-English languages. The other is translation training, which translate English labeled data to target languages, then leverage only translated data, or mixed English and translated data for fine-tuning. With the powerful transfer capability of the latest cross-lingual pre-trained model, the zero-shot training and translation training already show very good results in many tasks, like the cross-lingual test classification task. However, the performance on MRC task is not that good, and there are clear challenges for MRC task due to the characteristic of the sequence labeling tasks. To summarize, there are four major types of challenges of the baseline approach for cross-lingual MRC in non-English languages. The first challenge is that the language transfer capability of the cross-lingual pre-trained model is not sufficient for the sequence labeling task, which target precise phrase boundary detection. Here is one intuitive analysis between MRC task and one well-known classification task, NLI task, which is to predict the relationship between two sentences, such as entailment, neutral, and contradiction. In the analysis, it fine-tuned the cross-lingual pre-trained model with English labeled data for MRC and NLI task, respectively, and then test on non-English language directly. The table shows that the gap between the target languages and English on MRC task is significantly larger than NLI task. So for phrase boundary task like MRC, better semantic alignment among different languages is required. The second challenge is regarding machine translation quality. For MRC task, when translate English label data to target languages, we will translate both question and the long passage. So the translation noise will be more likely to be expanded, thus influence the original relationship between question and passage. Besides of question and passage translation, for MRC, we also need to translate the answer span to the target languages. Usually, passage and answer span will be translated separately, so it's challenging for answer span alignment in the translated passage. Here's one example. For the question, where is the Earth during the full moon? The correct answer span is highlighted phrases with a green color in this passage. After translation, for the passage and the answer span, we could see that the translated answer span has misalignment with the correct span in the German passage. Thirdly, in some cases, machine translator is not available, or the translation quality is too bad to tolerate for some tail language. Then leveraging translation data for model enhancement is not a good option. So, is there other data augmentation approaches beyond the machine translation? Finally, since MRC task requires to extract the direct answer span from the passage, it is critical for the precise answer boundary detection. According to the error analysis on ML-CUNY for zero-shot cross-lingual pre-trained model, the major error comes from the answer span partially overlap with the golden span, like the two cases in the left table. The ground truth for the first case is Ken-David. However, our model predicts David together with some redundant phrases as a result. The ground truth for the second case is 50 to 100 milligram. However, our model predicts a partial span 100 milligram as results. Taking Spanish and German as an example, the partial overlap of the golden span accounts for as high as 66% and 75% in all model prediction error respectively. So it's important to enhance the answer boundary detection capability of the cross-lingual MRC model. There are a series of recent works to address these challenges. In the following part, we select representative works to address each challenge for detailed introduction. These works could be categorized into the model transfer and data transfer approaches. To echo the language scaling approach introduced by Daxin in the first part, these advanced approaches for cross-lingual MRC belong to contextual embedding-based model, with or without parallel data. To enhance the semantic transfer capability of the cross-lingual pre-trained model, we will introduce three major approaches which leverage the machine translation data to design three novel model training methods for better cross-language transfer. The first work proposed a new task called Mixed MRC task with machine translation data to enhance the semantic transfer. Here's a graph to show the mixed MRC data generation. For the source English question passage pair, they will translate them into target language, like German. Instead of directly use the German query and German passage, they further mix them together QP pairs in mixed language. That is a German query with English passage, English query with German passage. The intuition to design this mixed MRC task is that, for our human, if someone truly understands two languages, they could well perform the more challenging MRC task in mixed languages. So with infusion, the challenging mixed MRC task for model training, we expect to further enhance the transfer capability of the cross-lingual model, since it could do a more difficult task. This mixed MRC task is infused as one auxiliary task of the main MRC task in fine-tuning stage. Compared with zero-shot training, we could see that there are decent EM and F1 metric gains for Spanish and German on MLQing, no matter use multilingual BERT or XM as backbone model for fine-tuning. The second type of approaches design the dual language encoders for better semantic transfer. The dual BERT is proposed on EMLP 2019 to make use of the representations learned from the source language, say English, to help the target language understanding. There are two encoders for both the source language and the target language. Specifically, it injects the information from the source language into the decoder of the target language to help boost the model performance on the target language. From the results in the right table, we can see that dual BERT achieves good gains on the cross-lingual MRC task compared with the baseline methods. Either use target language-specific BERT model for fine-tuning or use a multilingual BERT for fine-tuning. Since dual BERT injects information from the source language into the final decoder of the target language, which is kind of the later stage of the model training. It doesn't leverage the deep intrinsic relations between two languages. To further address this, another dual encoders-based model called filter is proposed, which leverages the translated data to enforce fusion in early model training stage between the source and target languages for better cross-lingual language understanding. As illustrated in Figure C, filter first encodes a translated language pair separately in the first M shallow layers, then performs cross-lingual fusion between languages in the intermediate K layers, and finally encodes the language-specific representations in deeper layers. Compared to the translation train baseline in Figure A, filter learns additional cross-lingual alignment across different languages. Furthermore, compared to simply concatenating the translated language pairs as input like Figure B, filter strikes a well-measured balance between the cross-lingual fusion and individual language representation learning. From the results, we can see that filter achieves the best results in the cross-lingual MRC benchmarks. Comparing with the multilingual BERT, XM Robota baseline methods, either using zero-shot training or translation training. The fourth approach, published on AAAI 2021, proposed an adversary training method to bring the embedding of different languages closer to each other to achieve better cross-lingual transfer. Specifically, in addition to the normal Q&A loss, an adversarial loss is introduced to make the embedding across different languages closer, which is try to fall a language classification discriminator. From the result, we can see that the adversary training brings gains across all language on ML Q&A, which shows that the better alignment through multilingual adversary training could bring the better language transfer capability. As we mentioned at the beginning, the machine translation data quality also brings challenges for the cross-lingual MRC task, since both the query and long passage need to be translated, which will bring the expanded noise. And it's also challenging for the alignment of the translated answer span with the translated passage. Next, 3 representative works will be introduced for the MT quality challenges. To reduce the negative impact of the noisy MT data, a novel language branch knowledge distillation was proposed in the work published on the Recording 2020. The core idea is to leverage multiple teacher models for kind of a smart assembling to overcome the MT noise. To train the multiple teacher models, they leverage machine translation to generate the so-called language branch MRC datasets. To be specific, they firstly translate the English question passage pairs into different target language, like Spanish and German. Then they group the question passage pairs according to the passage language. For example, for an English passage, it could be paired with its English question and also the translated Spanish and German questions. With this approach, they build up the language branch MRC datasets and leverage the language branch dataset to train multiple language branch teacher model based on the cross-lingual pre-trained model. These language branch teacher models could predict the soft labels for all the training data, respectively. The authors also designed a smart model score assembling method to weighted sum up the prediction scores by the teacher models. And finally, leverage the soft label data to distill a student model. For the result on both MLQA and F-squad, the language branch approach all achieved SOTA results. When assembling the scores by multiple teacher models in language branch MRC work, each teacher model is using a same weight for all instances. However, for different instances, the performance of the teacher model are likely to be different. Thus, the optimal approach is to assign different weights for each teacher model at instance level in order to get the best assembled soft labels. With this motivation, our team's work in KDD' 2021 proposed to leverage the reinforcement learning for the multi-teacher selection at the instance level. Specifically, an agent is introduced to take action to decide whether to select each teacher model or not for each instance. Once the teacher model are selected, the assembled soft labels will be used to optimize the student model. After train the teacher model, we will evaluate on the golden label test sets. The metric is treated as a reward to further optimize the agent to make a better decision in the next iteration. In this way, the method is able to select the most suitable teachers at the instant level. Here are the comparison results. Compared with the static assembling approach, the RL-based teacher selection at the instance level achieves the significant gains. The paper also started 3 different reward functions by considering different methods to calculate the student model performance, including using cross-entropy, MSE loss, or performance on dev set instead of the training set. Across all the reward calculation settings, the ILKD achieves the best results. As we mentioned previously, for MRC data translation, since passage and answer span are usually translated separately, it's very likely that the answer span after translation may not exist in the translated passage or have some boundary errors. To address this challenge, the work published on EMLP 2019 proposed 3 approaches for the answer span alignment after translation. The first approach is a simply match. They calculate the character level test overlap, see the F1 score between the translated answer span and the arbitrary sliding window in target language. Then choose the sliding window candidates with the best F1 score as a final answer span. The second approach is called answer aligner, like the middle graph of the figure 1, where they feed the translated answer span and the target passage into the board model. The model will learn the semantic relation between them and generate the improved answer span for the target language. The third approach is called answer verifier, like the rightmost graph of the figure 1. On top of the answer aligner approach, it further infuses the query test into the target language into the board model and verify the translated answer span correctness and generate improved span for the target language. Here are the experiment results. Use different alignment approaches. Without using any answer span alignment approach, we could see that all the metrics are pretty low. By using the simple match, aligner, and verifier, the EM and F1 get a significant boost. Among the 3 approaches, the verifier achieves the best result. It's kind of aligned with our intuition, since all the information in target language, including query, passage, and translated answer span, are all used for the verification and the span improvement. To address the availability issue of MT data, we could consider to leverage other types of data for augmentation to enhance the model performance, like the unlabeled language-specific data and the generated language-specific data. Let's look at some representative works. As we know, the language-specific labeled data, for example, the non-English question, passage, answer span data, is hard to get or very limited. However, the real language-specific data without label is relatively easy to get in many application scenarios. So could we leverage this large-scale unlabeled language-specific data and generate good labels for the cross-lingual model training? The recent work we published on KDD 2021 designs an iterative knowledge distillation approach to derive high-quality labels for these unlabeled data in the target languages for better cross-lingual transfer. Specifically, a M0 model is trained using existing labeled data in source language like English. Then this model is used as teacher model to infer soft labels on the unlabeled data in target languages. After that, this new data could be used to distill a student model, M1, using knowledge distillation. It's expected that the soft labels may contain lots of noise. To reduce the noise, a reinforcement learning-based selective knowledge distillation approach is proposed, which I will introduce later. The M1 model will have better performance on the target language after this stage. Then it can be further treated as a better teacher model to infer on the unlabeled data to get better soft labels. Then another M2 model can be trained use the RL selective KD. The process can go for the several rounds until convergence. So we can see the model training is a kind of iterative process. Now let's look at the IL selective KD on the right part of graph. A policy agent is introduced to select high-quality training cases from the target language data. The selected data is leveraged to distill the student model. After training, the performance of the student model is further taken as reverse to feedback to the policy agent in order to optimize the agent to make better decisions in the next rounds of training. The policy agent and student model are trained round by round to derive better performance in the target languages. From the result, we can see that this iterative knowledge distillation approach achieves sorted results on 2 benchmark datasets for NER tasks, which proves their capability to leverage unlabeled target language data for better transfer. This iterative knowledge distillation approach is also straightforward to be extended and applied to the MRC task. Another data transfer approach is to leverage generation model to generate synthetic data in target languages. In terms of MRC task, the language-specific passages are easier to get. For example, we could extract large-scale passages in target languages from the wiki pages. Given the language-specific passages, the multilingual generation model like MT5 can be used for generating question and answer spans. To be specific, at the first stage, the MT5 is fine-tuned on the English scored datasets. Then the fine-tuned model is used to generate question and answer spans on the target language passages. In this way, large amount of synthetic training data in target language can be used to fine-tune the downstream MRC models. As shown in this table, the model performance on X squared can be boosted significantly when adding the target language synthetic data for MRC model fine-tuning. The fourth challenge is how to further enhance the answer span detection for cross-lingual MRC model prediction. I will introduce two representative works for this. Since the answer spans extracted by MRC models are mostly entities on meaningful phrases, the work published on ACL 2020 proposed a scalable approach to mine the large-scale knowledge data from web pages and leverage this knowledge data to design a language-agnostic knowledge masking task, short for LAKM, to introduce the language-specific boundary pra-knowledge into the model. Here, the knowledge data is not limited to entities. Instead, it includes all kinds of meaningful phrases. Given a user query, the authors leverage search engine to get the top-ranked URL and use the URL titles to firstly extract the commonly occurred phrases as candidates, then design more features to finally decide the truly meaningful phrases. This knowledge data mining process is language agnostic. With the knowledge data in various languages, the author designed a language masking task as one auxiliary task of the main MRC task in the fine-tuning stage. Here are the experiment results on MLQA and MTQA. We can see that by adding LAKM task, the EM and FI scores have significant improvement. Besides of knowledge infusion, the other work published on Wisdom 2021 proposed a two-stage approach for boundary refinement, which is inspired by how we humans write articles. Let's look at the leftmost case for the main idea. Given a query and passage pair, firstly use a base module to get the draft answer span, which probably have some boundary detection error. Then leverage a calibration module to further refine the boundary and get the final calibrated answer. The whole process is called calibration network. The right graph shows the detailed model architecture. The base module could be whatever MRC model we already have. The challenge is that how to collect train data for the calibration module training, especially for those non-English languages. To address this challenge, this work leverages a wiki document to synthesize large-scale training data in multiple languages and design a novel phrase boundary recovery task to pre-train the calibration module. To be specific, in wiki, there are lots of hyperlinks for the meaningful phrases or entities. The authors extract these linked phrases as golden answer spans and gobble them by some operations like delete, add, shift some words to synthesize noisy answer span, entity spans. Then for the phrase boundary recovery task, it will take this noisy entity span as input and the original hyperlinked phrases as ground truth for the denoisy pre-training. According to the result on MLQA, the average F1 and EM scores across all 7 languages have significant gains by adding the calibration module. Since the calibration module is orthogonal to all existing MRC models, so it could be easily added on top of all previous MRC work to bring the actual gains. Here are the key takeaways. MRC task is more challenging in language scaling, as the baseline approaches that see the cross-lingual pre-trained model plus machine translation data for zero-shot or translation training don't work sufficiently well due to 4 major challenges. Firstly, to address the insufficient transfer capability of the cross-lingual pre-trained model. By leveraging the machine translation data, the new mixed MRC task, dual encoder-based model, and multilingual adversarial training approaches are proposed to enhance the semantic transfer capability across languages. Secondly, to reduce the negative impact of the machine translation data noise. Multiple teacher models trained with language branch MT data are used for the soft label assembling to reduce the MT noise. Besides, the reinforcement learning-based best teacher selection at instance level could further reduce the noise for better student model training. And to deal with the answer span alignment issue after machine translation, the back translation plus verification is proposed to improve the answer span alignment quality. Thirdly, to address the unavailability of MT data in some cases, we could also leverage unlabeled language-specific data as the generated language-specific data for the data augmentation. Finally, to enhance the answer span boundary detection, the new LAKM task is designed to infuse the language-specific boundary prior knowledge during the MRC model training. Besides, the calibration network is proposed to add a new calibration module on top of existing MRC model to refine the answer span boundary. Now, there are still many ongoing efforts to continue to address these challenges in order to further boost the cross-lingual MRC model performance for all languages. We are looking forward to more breakthroughs and also more discussions on this in the near future. Okay, that's all for the MRC part. I will hand over to Linjun for the next application, grammar error correction. Thank you.
Thanks, Ming. My name is Linjun Shou, applied scientist from Microsoft. Next, I'll take the cross-lingual grammar error correction and question generation as applications for language scaling. So referring to the categorization of NLP tasks in Daxin slides, grammar error correction refers to token-level text generation in natural language generation, while question generation refers to sentence-level text generation in NLG. I'll give the detailed task definitions in later slides. So first, what is grammar error correction? Grammar error correction is the task of correcting different kinds of errors in the text, such as spelling, punctuation, grammatical, and word choice errors. So the table here lists one example. The input is, she saw Tom is catched by a policeman in park at last night. Clearly, this sentence has errors. And the output is the correct sentence. She saw Tom caught by a policeman in the park last night. And then what is the second task, question generation? So question generation is the task of generating a question based on passive context and the input answer. So the table here also lists one example. So the input passage is talking about European Union law, which have been transposed into laws of member states. And the European Commission can take the proceedings against member states under the Treaty of the Functioning of the European Union. And the input answer is Treaty on the Functioning of the European Union. And the reference question generator of the model should be, under what treaty can the European Commission take actions against member states? And this QG task can be treated as sentence level generation because the generated question is quite different with the input passage or the answer, while the previous QGEC task, majority of tokens still is the same of the input sentence. Okay, so we could categorize the approaches cross-lingual GEC and QG into two parts, model-based transfer and the data-based transfer. And in terms like model-based transfer, it can leverage monolingual data as well as parallel corpus. And in terms like database transfer, it consists various methods, including back translation, synthetic data construction, etc. And next, we will pick some of the representative works to introduce these methods. So first, let me introduce model-based transfer. Chi et al. Proposed XNOG model, which is an encoder-decoder architecture for the question generation task. It will take the input sentence with grammar errors as input, and the decoder is supposed to output the correct sentence. XNOG proposes two stages of pre-training for both encoder and decoder, and there are several pre-training tasks for better cross-lingual transfer based on both monolingual corpus and parallel corpus data. So first is encoder pre-training. XNOG uses transformer as a backbone architecture of the encoder, and the mask language model and the cross-lingual mask language model are leveraged to pre-train the encoder. Specifically, in terms of monolingual data, random masking is applied to the original sentence, and the encoder is trained to output the correct tokens of the masked positions. And in terms of the parallel corpus, the parallel sentences are first concatenated together with random masking and feed through the transformer encoder, and then the encoder is optimized using cross-lingual mask language model objective to output the correct tokens in the masked positions. These two tasks are trained jointly using multitask learning. It has been shown in cross-lingual NOU models such as cross-lingual language model and Unicoder. These two tasks could achieve total cross-lingual encoder results. So next is decoder pre-training. First, decoder is also leveraging the same transformer architecture as the encoder, and it is firstly initialized with the pre-trained weights of the encoder after the cross-lingual mask language model and the mask language model pre-training. And to further continue pre-train the decoder, the parameters of the encoder are fixed, and two sequence pre-training tasks are used to pre-training by leveraging monolingual data as well as parallel data. And for the monolingual data, the pre-training objective is DAE, which is short for denoising autoencoder. Basically, three types of noises are used to obtain the perturbed text, including word order is locally shuffled, and the randomly dropped tokens with their probability equals to 0.1, or substitute tokens with a special padding token P with a probability equals to 0.1. And the model is trained to recover the original text condition of this noise text after these three types of denoising operations. And in terms like parallel corpus, machine translation is treated as the XAE task, which is short for cross-lingual autoencoder, by translating from two directions, both from language X to language Y or language Y to language X. And then the model is evaluated on cross-lingual question generation task, whereby only using English question generation training data, the model is expected to generate Chinese questions given Chinese paragraph and input the answers in Chinese. The work compared with three baseline methods: X language model, which is a fine-tuning XLM model with the English QG data only, and the pipeline XM, which is the pipeline approach by translating the input Chinese sentences into English first, then performing English to English question generation with the XLM model, and finally translating back the answer to Chinese. And for in-term translation, a transformer-based translator is trained on the multi-UniYuan dataset. And the third approach is pipeline XM with Google Translator. And the method is same with the previous one. The only difference that in terms of translation model-wise, they leverage the Google Translator as their default translation model. And from the results, we can see that XNOG retrieves significantly better results compared with these three strong baseline approaches. Besides, the authors also further conduct human evaluations based on three factors: relevance, fluency, and correctness. And from the table on the right, we can see that XNOG also achieves better results in terms of relevance and correctness. And in terms of fluency, the model also achieves very good results. And the very best result is with the Google Translation version, which is expected because Google Translation is a very sought translation service built by Google. And another model-based transfer is Martin-Lingo-BART. Different with the previous work, XNOG, Martin-Lingo-BART directly uses sequence-to-sequence pre-training for both encoder and decoder, rather than two-stage pre-training. And the pre-training is called multilingual denoisy pre-training on monolingual data only. Specifically, it also injects noises into the input instances, and encoder encourage the model to recover the original text. In terms of noise function, Martin-Lingo-BART contains two operations. Mask 35% of the words in the input sentences by rendering, sampling, and span length according to a Parsing distribution. And the second is sentence level permutation by permute the ordered sentences within each instances. And a new training corpus called CC25 is used for pre-training, which contains the monolingual data of 25 languages. So Martin-Lingo T5 is also another work in line of the model-based transfer by leveraging bigger models and bigger corpus. From the table below, we can see that Martin-Lingo T5 is also an encoder-decoder based model, similar to Martin-Lingo-BART and the XNOG, as I mentioned earlier. But the model sizes actually increased a lot from like previously it's like Martin-Lingo-BART is 680 millions. Now it is increased to 16 billion parameter size, which is a larger version of the Martin-Lingo T5 model. And it covers 101 languages rather than 25 languages in Martin-Lingo-BART. Actually, Martin-Lingo-BART can be seen as the Martin-Lingo version of T5 using a new training corpus called Martin-Lingo C4 in 101 languages. Figure 1 shows the training data distributions in different languages. During training, Martin-Lingo T5 also leverages upsampling and downsampling mechanism to balance the training data sizes across different languages. Okay, so in terms of like pre-training tasks, T5 has a comprehension study of various pre-training objectives for sequence pre-training as shown in the first table. For example, they have conducted prefix language modeling, which is very similar to GPT style pre-training. Basically, it takes the input of first a few words of the input sentence and the target to output the later tokens of the sentence. And also it includes bird style pre-training, which by randomly masking some tokens of the input sequence, and the target is to output original text. And also it includes reshuffling by shuffling some text pieces of input sequences, and the model is encouraged to output original text. And also others like math style and replace spans, drops tokens, or random spans. And they conduct various experiments comparing this kind of pre-training tasks for sequence pre-training. And actually, the bird style method shows the decent but the best results on various NOU tasks. So this work also pre-trains 5 versions of Martin-Lingo T5 models with different parameter sizes ranging from 300 millions to 13 billions, which are named as Martin-Lingo T5 small, base, large, extra large versions. And these 5 models are evaluated on various datasets, including question answering, sentence pair matching, cross-lingual named entity recognition, etc. And the Martin-Lingo T5 achieves total results across various settings, including zero-shot transfer, translation train, and in-language multitask learning. Namely, the models are fine-tuned on golden data in all target languages. Another finding is that larger models with bigger datasets achieve better results. The performance has a positive trend from small to large models in terms of the same architecture of Martin-Go T5. And this paper also points out an interesting finding in terms of zero-shot experiments. There could be illegal predictions, including normalization, grammatical adjustment, and accidental translation. And the table on the right lists some cases of these three illegal predictions. Normalization is kind of like a casing problem of the translation of the generation. And the grammatical adjustment is like grammatical errors in the generated questions or like GEC version. And for the accidental translation, it's kind of interesting. For example, the model is back to output Chinese sentences, and it may include some tokens in other languages other than Chinese. And to mitigate this issue, this work also proposed to combine with pre-training tasks during the fine-tuning stage as kind of the multitask learning, which is quite effective. Next, let me further introduce the database transfer approaches for cross-lingual GEC. First is domain adaptation. Racha and al. Propose a simple recipe for multilingual GEC. It includes 3 stages of training. First, multilingual T5 pre-training, which is pre-trained on general domain corpus. Second, GEC pre-training by adapting the general MT5 model to GEC task. Multiply common GEC errors. The denoising pre-training contains dropping spans of tokens, swap tokens, drop spans of characters, swap characters, insert, lower and uppercase of words. And the last stage is GEC fine-tuning on GEC downstream dataset. This work takes MT5 base and access large versions for experiments. From the results, we can see that the model performance on 3 non-EN languages shows total results. Especially, the access large version even has better performance than ensemble-based methods. In terms of GEC pre-training stage, Shou et al. Further conducts an empirical study about how to better incorporate the synthetic data by answering 3 questions. First, how to generate better studio data X. Second, seed corpus selection. Will clean data lead to better performance? What's the correlation of model performance with the grammatical complexity of the seed corpus? 3. Joint training or pre-training. Joint training means that the synthetic data is combined with real GEC training data for joint learning. Pre-training means that the synthetic data is first used for pre-training. Then the model is further fine-tuned using GEC training data only. For the first question, how to generate better studio data? This work experiments with 3 approaches. First, direct noise. It injects noise directly into the input sequence sentences. Second, back translation noisy. Actually, it trains a sequence model to generate noisy sentences instead of directly adding those noises, given grammatical correct sentence. And during the decoding stage of the sequence model, it leverages noisy method to generate noisy contents. And third, back translation sample. And similar with the back translation noisy, it also trains a sequence model to generate noisy sentences. Difference is that during the decoding stage, it uses random sample from the beam search results. From the table here, we can see that the simple direct noise shows better performance compared with the other 2 back translation-based approaches in terms like fluency score. The second question is how to select seed corpus. To answer this question, this work experiments with 3 corpus, which is Simple Wiki, Wikipedia, GigaWord. And from the table here, we can see that Simple Wiki has the most simple grammar compared with the other 2 datasets, while GigaWord has the most cleanest text compared with the others. And they conduct experiments on 3 datasets using 2 data generation approaches, back translation noisy and direct noise. And across these two generation methods, the GigWord cleanest text shows better results than the Wikipedia and the ThinkWiki corpus. The third question is to whether use joint training or pre-training when leveraging the synthetic GEC data. The authors experiment with two data scale, 1.4 million versus 14 million. As shown in this table, when the scale of synthetic data is small, there isn't clear difference between pre-training and joint training. However, when they are extensive with synthetic data, the pre-training is more effective in order to better leverage it. So this proves that pre-training is crucial for leveraging extensive Xiubo data. And when the data scale further increases from 10 million to 70 million, we can see in the curve here, there are clearly increasing trends for both direct noise and the back translation generation methods. Specifically, there's a big jump from 0 million to 30 million. However, after the data size becomes big enough, like 30 million, the curves gradually flatten out. This shows that the noise of the synthetic data may limit the upper bound of the performance gains. Another method of database transfer is to leverage data from similar languages. Yamashita et al. Proposed experiment to verify whether similar languages could lead to better transfer. In the GEC three-stage training framework, they also add source language learner corpus in the GEC model training, which is the second stage. To study the impact of language similarity, 4 languages are chosen, namely Russian, Czech, English, and Japanese. And the left table summarizes the language similarity relationships between these 4 languages. And they pick Russian and Czech to evaluate GEC performance and use the other languages as source languages to transfer from. From the left table, we can see that Russian and Czech are most similar languages. And in the table on the right, we can see that Russia GEC using Czech as source language shows the best performance, and vice versa. This shows that better transfer can be achieved for similar languages. Besides, they also compare with translation language model and the master language model for pre-training, and TLM shows better results than a master language model, which further shows that parallel corpus have better transfer. Okay, so here are the key takeaways of this session. First, model-based transfer. Multilingual denoising pre-training is effective for cross-lingual sequence pre-training. Parallel corpus have better language transfer, and bigger model and larger data lead to better performance. And in terms of like database transfer, GEC pre-training on top of existing general pre-training could further boost the model performance. Okay, so next, let me hand over to Dr. Jian to give us summary and future directions of language scaling. Thanks.
Hello, everyone. I'm Jian from Simon Fraser University. Now, let me wrap up the tutorial today. In today's tutorial, Daxin first motivates the need for language scaling. Indeed, multilingual language scaling is needed in many applications. And he also gave the problem formulation and discussed the technical challenges. In terms of methodology, Daxin talked about 2 major approaches: model transfer and data transfer. Then, Xiubo, Ming, and Linjun talk about 3 example applications, namely dependency parsing, machine reading comprehension, and grammar error correction. Those applications use model transfer and data transfer. Through this discussion, I hope that you agree that language scaling is critical in business and many applications. The key challenge in language scaling is the lack of cross-lingual data. Although we may have sufficient data in some big languages where they are popularly used, but we may not have sufficient data for many languages that are not popularly used. In terms of applications, they can be divided into two major types: natural language understanding and natural language generation. And then further divisions of the application categories are also discussed. Then we discuss two major categories of methods: data transfer and model transfer. Indeed, those two kinds of methods have to be combined in many applications. Using dependency parsing, machine reading comprehension, and grammar error correction, we illustrate how the two ideas, the two major methods, can be used in them, and how the two major methodologies can be integrated in those applications. As you can see, language scaling is a very important, very hot area in industry. Naturally, after this tutorial, you may ask, what would be the future directions of this important field? In fact, there are still quite many questions that have not been solved, and they are good for future direction. First, in language scaling, how we can systematically integrate more linguistic knowledge into language scaling is an important issue. We know that languages are very different in morphology, syntax, and semantics. Therefore, the essential problem for language scaling is to bridge the gap between languages in all these linguistic features. Although the current approaches of model transfer and data transfer have proved effective in many cases, the empirical studies also show that the performance of transfer models may not be satisfying when the target language is distant from the source language, or the resource for target language is extremely low. To address this challenge, we may have to consider integrating linguistic knowledge into our data-driven approach. Let me give one example to illustrate. The efforts of universal prose tagging and universal dependency parsing want to set up standard syntax analysis schemas across all languages. In this way, all languages can represent their syntactic structures using a uniform schema. These efforts can definitely help to universalize the language representations. But at the same time, more and more topological databases are available now, such as the Word Atlas of Languages, Xiubo, Etholog, and so on. Currently, we only see some very early works using these databases to measure the distance between the languages. And a lot of work may further use the measured distance to select the intermediate transfer languages. However, at the global picture, we still are looking for systematic methods that can integrate linguistic knowledge into transfer approaches. The second important direction is the best practice to train multilingual models. As we explained in the previous discussion, in order to save the maintenance cost, in practice we usually build a universal model to support multiple languages. Then, we'll get a series of questions about training this universal model. For example, when transferring from the source language to multiple target languages, the model tends to overfit on new data, but loses the useful information learned from the earlier data. This problem is sometimes referred to as the catastrophic forgetting. Therefore, one important question is how we can deal with this forgetting effect. Moreover, linguistic studies have grouped languages into hierarchical families. As you can see, the picture on the slide shows an example for the family of Proto-Indo-European languages. Intuitively, it is easier for languages in the same family to transfer the knowledge because they share more topological structure. Therefore, it makes more sense to put languages in the same family into a single universal model. However, there are very few efforts to verify the effectiveness of this assumption at large scale. Even if this assumption is true, it is still not clear how to choose the level in this hierarchical family tree to group the languages in the same model. Another interesting question is how to measure the capacity of models versus the size of languages. We can imagine that when we put more languages into a single universal model, it needs more parameters to capture the variations in the data. However, we don't know how to measure the model capacity or the language size so that we can determine the best combination of languages in the same model. We believe that there should be more theoretical or empirical studies to give us answers or guidance to these important questions. Thank you for attending our tutorial. We hope the tutorial and the associated materials will help you to enter this interesting and exciting field. Bye.